Welcome back to data mining. In this module, we'll talk about linear models. Here is what you will learn in this module. We will first discuss what a linear model is, and we will look at its mathematical background. Then we will determine when linear models are appropriate for data analysis, and we will use simple linear regression and multiple linear regression to build a model of any data in any dataset. We will then analyze the data in R and Python with simple and multiple linear regression, and we will evaluate the models that we have built with important quality metrics. So first we're going to talk about linear modeling with regression. Regression allows you to estimate how a dependent variable changes as the independent variable or variables change. Input variables are called predictors. They are typically numeric and continuous, and the output variable, also called the response variable, is also typically numeric and continuous. When analyzing the data, regression comes up with a function or a model, which is what we're seeing here in this yellow box, based on the predictor variables that provides you with the best fit line or curve for the response variable. Now, it's important to understand that any response variable that the model calculates is, in fact, the result of the model and not of actual reality. So, regression models describe the relationship between variables by fitting a line to the observed data. Linear regression models, such as simple and multiple linear regression, use a straight line. That's what we can see here with the equations. For simple regression, we have one input variable with one coefficient m times x plus b. With multiple regression, we have multiple input variables. We have an x1, we have an x2, and we also have multiple coefficients, m1 and m2, and so on. Now, logistic and nonlinear regression models use a curved line, which is what we will see later. All in all, though, regression allows you to estimate how a dependent variable changes as the independent variable or variables change. So let's look at simple linear regression now. We use simple linear regression to describe the strength of the relationship between two variables. We can also use it in order to predict the value of the dependent variable at a certain value of the independent variable sometime in the future. This here is our basic equation, and in order to arrive at this equation, we have a number of assumptions. The first assumption is called homoscedasticity, which means that the error in our prediction does not change much across the independent variable. The second one applies typically to multiple regression, but it's really the independences of observations, meaning that there are no hidden relationships among the predictors themselves. Then thirdly, we want to ensure that the data follows a normal distribution, and fourthly, that it lends itself to a linear analysis. So let's assume that we work for a manufacturer of personal wellness products, and that it is our job to forecast the sales of bottles of sunscreen based on the forecasted hours of sunshine for a week. Here, our X attribute contains the hours of sunshine from Monday through Friday. And in our Y attribute here, we have the historical sunscreen sales also on a Monday through Friday basis. We see that our N is 5 because we have 5 numbers here. How do we arrive at our equation in the format of Y equals mx plus b? Here's how. So for each x and y point, we have to first find our x squared and our x times y, which is what we're doing right here. Then we're going to sum all of these, which gives us our sum of our x, our sum of our y, our sum of our x squared, and the sum of our x times y attributes. From our previous page, we remember that we are looking for y equals mx plus b. We have these values calculated that we need in order to calculate our slope, our intercept, and then assemble our entire equation. And we also know that our n, that is the number of data points that we have, is 5. So first we're going to calculate our slope m. Our slope m equals the number of data points multiplied by the sum of our x and y attributes minus the sum of our x attributes and the sum of our y attributes. We divide that by our n multiplied by the sum of our input attributes squared minus the sum of our input attributes, and that as a square. So that gives us these numbers here, and we end up with an m value of 1.5183. The next thing we calculate is our intercept. In order to calculate our intercept, we need our m value here. This is why we're calculating the slope first. So our intercept b equals the sum of our y attribute, the sum of our dependent attribute that is, minus our slope m times the sum of our input attributes. And we divide all of that by the number of data points n. So that gives us 41, which is this here, minus 1.5183, that's our m here, times the 26, and that divided by 5. That gives us 0.3049 as our intercept b. Now we're going to assemble the equation for our line y equals mx plus b, which gives us y equals 1.5183 times x plus 0.305. Now that we know what our model looks like, namely y equals 1.518 times x plus 0.305, we can calculate the dependent variable values based on our model. And we're seeing here that the output that we're getting from our model is different from our actual reality. We call this difference the error, and this error will become important in a little bit. But what's important is that if the weather forecast now predicts 8 hours of sun, we can now use our model to predict the following sales. We can say 1.518 times 8 plus 0.305 gives us 12.45 bottles of sunscreen that we can sell. And if we want to see this on this graph here, all we have to do is just make a line here with our 8 hours, our input attribute, and it will intersect our model line, our best fit line right here at 12.45. So previously we've seen that the y values, that is the dependent variable values that our model calculates, are different from the y values, that is the dependent variable values that we know from reality, right? So how do we get to this fit line at all? Well, we get to this fit line by making the total of the square of these errors as small as possible, and that's how our fit line becomes optimized. So that when we square each of those errors and we add them all up, the total is as small as possible, and that's what we call the least squares. Now, these errors here are also called residuals. A residuals is a measure of how well a line fits an individual data point. Residuals should do the following. They should center around 0, they should follow a normal distribution, and they should not follow any pattern. How can we tell? Well, we could turn our diagram such that our fit line in fact becomes our 0 point line, our y line, and then we look at the distribution of the errors on each side. Does it center around 0? Do they center around 0? They sure do. Well, do they follow a normal distribution? Well, just about, right? Then do we see any detectable pattern? Not at this point, because we have 3 on one side, 2 on the other side, and none of these have the same value or the same distance from the 0 point. So this regression model looks to be of good quality. Let's see what a simple linear regression looks like in R. A simple linear model in R is pretty straightforward. We're starting with a test for our attributes that we want to compare. Here we're using 2 numeric attributes, education years and income USD. Always test before you assume. And then we're going to set up our plot. This is a basic scatter plot to ensure that there is some relationship. We're seeing there is some relationship that we might assume would be worthwhile. And then we're going to set up our model. The linear model is set up such that we use our LM linear model function, and then we exercise that function on our dependent attribute that we're going to map on our independent attribute with the tilde here. And then we're going to specify what the data frame is that we're applying this linear model to. And then we are going to use the summary function right here to pull the output out of our linear model, and this is what the output looks like. Let's look at that in detail next. Let's take a look at our output now. Each output always starts with the formula that caused the results that we're going to see below. Here we're seeing that the formula is the one that we programmed in to generate the output, namely income USD being mapped with the tilde on hours per week for the data frame of adult. So now let's take a look at the residuals, which we know indicate the health of our model. Typically, we want our residuals to center around 0. Well, our median is at minus 15,109. That hardly is 0. Okay, then we would want our residuals to follow a normal distribution. Let's take a look at the min here at minus 79,013 and the max at plus 179,002. So that also does not really look like a normal distribution. At this point, we would want to check whether our residuals follow any pattern in terms of testing the heteroscedasticity. Really, we might do that by plotting the residuals on any kind of attribute. Most likely that is going to lead to a confirmation of what we are seeing already here, that our model is not optimal. The next part of our output is the coefficients here. For the coefficients, we're seeing our first column contains the estimate. The estimate is the expected value of, for our intercept here, income USD when we consider the average income USD in the data set. And that is followed here by the estimate for hours per week that is based on the average of that attribute. In the next column, we're seeing the standard error. The standard error is the average amount that the coefficient estimates vary from the actual average value of our response variable. So here the standard error of 824.77 for the intercept is quite sizable. Well, let's take a look at the next column, which is the t-value. The t-value is a measure of how many standard deviations our coefficient estimate is far away from 0. Well, typically in a situation in which we're testing against a null hypothesis, we want this to be far away from 0. Here, the t-value really is not of that much importance, other than that we have some standard deviations going on here that are really quite big. Let's take a look then at our last column here. That's the probability of observing any value that's equal or larger than t. That's kind of like the p-value here in our regression analysis. We're seeing that, of course, this is a very small value, and that's what we're looking for in a p-value if we are looking to reject any kind of null hypothesis. Well, okay, our linear regression equation then, y equals mx plus b, comes out to this then. Our y, we know, is income USD, comes out to 725.27 times hours per week plus 27,255.66, and that's our linear model as we have set it up with our hours per week and income USD attributes. Next, we'll take a look at how good this model actually is. Now let's take a look at the last portion of our output. Here we're seeing our residual standard error, and we're seeing here as well that on 32,559 degrees of freedom, our residual standard error is 43,460. That's bigger than our degrees of freedom, which means we have a huge residual standard error. And if our residual standard error measures the quality of a linear fit here, it shows us that the average amount that the response variable will deviate from the true model. So this is a huge deviation that we have here. And our F statistic indicates if there is a relationship between the predictor and the response variables. We're seeing typically we want the F statistic to be far away from 1. It's pretty okay. And the p-value here looks pretty good as well. That's not surprising. But now let's take a look at the middle line here, which is the r-squared values. Now, we're not going to discuss the difference between multiple r-squared and adjusted r-squared. The values here are very similar. We do need to understand that any r-squared value measures how well the model fits the actual data. Typically, r-squared is expressed as a percentage, so this would be about 4% here for each of these measurements. And that means that only 4% of the variability of our data, of our income USD values, can be explained by the model, by the equation that we have generated. So, in other words, if our number is very close to 0, which this one is, that means that the model does not explain the variance in the response variable well. If our number were closer to 1, which would be 100%, our model would explain our observed variance in the response variable pretty well. Well, here, not so much. Let's see if there is maybe a different variable that we can work with. Let's see what a simple linear regression looks like in R. Here is what a multiple regression looks like in R. So first we're going to generate a clean adult 1 data frame in which we store only the numeric variables from our original adult data frame. And then we're going to test that. And we're seeing here with a summary function that we get the 5-number summary for each of these attributes, which means that they are all numeric. Next, we're going to plot them just to see what the distribution looks like graphically. And this plot function walks through each attribute, age, education years, and hours per week on income USD. What we're seeing here is instead of verbosely writing out each attribute by its name, we can just use the tilde and the dot, which literally maps the dependent variable on each of the other variables in this data frame. Here they are all the input variables. This is why we're seeing all the different plots here. And then we're building our model. Our model is adult1.mod1. We're going to build a linear model. The linear model is going to be applied to the adult1 data. But here now we are mapping income USD with a tilde on dot. Now the dot here means on all of the variables in the data frame, because more is better, right? Let's take a look at the output. Our regression output starts with the function call here. We see we have a linear model, and the formula is income USD is being mapped on dot, which is all the data in the data frame, and the data frame that we're looking at is the adult1 data frame. So, residuals. Typically, we want our residuals to center around 0. Do they center around 0 here? No. What about the normal distribution? That's our next criterion. Here we are looking at a minimum of 86, 153. We're seeing here that the max is 181, 174, even with a negative median, especially with a negative median here. That certainly is not a normal distribution. It's very skewed. So the residuals are telling us that the model that we're looking at is not very representative. Looking at the coefficients here, we're seeing that the formula that we're building is a multiple regression formula where our y, that is our income USD, is M1 times X1, so 580 roughly times age, plus about 4,500 times education years, plus 452 times hours per week, and then minus this intercept of 33,083.79. That is our multiple regression equation here. We're seeing we have a very large standard error here in the intercept, and although our p-value here seems to look pretty okay, let's take a look at the measure of a good regression equation, which would be the r-squared. Now we're seeing here our r-squared is at about 14%, which means that only 14% of the observed variation in income USD can really be explained by the model's inputs. Sometimes more isn't better, and sometimes more really is just more. Now let's look at linear modeling in a different data set, fuel efficiency in cars. The fuel efficiency data set is relatively small. It contains 38 observations, that's 38 rows of 8 variables. The 8 variables are miles per gallon, gallons per 100 miles, weight, displacement, number of cylinders, horsepower, acceleration of the car, and engine type, whether the engine type is a V or whether it's a straight engine. We're seeing here that all of the attributes are numeric. This is what they look like right here in a spreadsheet format. Let's explore our data set. Right from the start, we see that we have two attributes that basically say the same thing. When we plot GPM and MPG onto each other, we're seeing there is a definite relationship going on, so we can dispense with one of them. And just because we can, we are going to drop miles per gallon, and we're going to use GPM, that's gallons per 100 miles, going forward as our dependent attribute. Then we're going to set up a multiple plot environment, and we're going to plot all of the independent attributes upon GPM, which is what we're seeing right here. Here we're running our multiple regression again, as evidenced by the formula of GPM mapped on all the attributes in the data set. That's also what we're seeing in our regression output here. Then taking a look at the residuals, we're seeing that the median for the residuals is very close to 0. That's exactly what we're looking for. We're seeing here the min at about minus 0.5, the max at plus 0.6, so that's almost symmetrical. That tells us that the data are almost normally distributed so that we can give high credence to the model that we're going to look at. In terms of the coefficients, here we're seeing our estimate for the intercept and for the weight and the displacement and all of the variables, the input variables that we've looked at. We're seeing a very small standard error setting here, and we're also seeing the standard deviations at a very small numbers. That seems to be very good. Here we are looking at the p-values for each individual attribute in relation to our GPM. Now these are going to be interesting later on, but what we right now want to see is an R-squared value that is better than what we've seen before. And here, as we look at our R-squared values of whether multiple or adjusted, we're seeing that they are at 93%, which tells us that our model has high credibility. The next thing we want to look at then is how are our variables correlated, not just to GPM, but also to each other, because one of the assumptions for our regression is that the variables we're looking at have to be independent. For that, we are going to run a correlation on the entire data set that pulls in all the attributes, and we're seeing that each attribute is of course perfectly correlated to itself, but some other values also require more investigation. For example, displacement versus weight. We have a 95% correlation here. We have a 91, almost 92% correlation between weight and number of cylinders, and the same applies to weight and horsepower. So not all the attributes, the input attributes, are in fact independent from each other. This means also that we can very well reduce these dimensions that are dependent on each other so that we work with a smaller data set. What if we could run all the possible regression equation configurations in order to determine what the optimal number is of variables that we would need in our equation for a multiple regression? Well, we can. That's called the best subset regression. And here's what this looks like. We are going to use the reg subsets function from the leaps package, and then we're going to configure it to show us the best two parameters that we want to include in our equation, and for those to display the R-squared value, the adjusted R-squared value, and the CP value. This gives us this reg subsets, this regression subsets table with the intercept and with the independent variables horizontally, and with the number of variables that could be in our regression equation. Here it is displayed vertically, and 6 is of course all of the variables. So now, if we were going to build just a simple linear regression equation with one variable, we would want to pick weight, because weight has an R-squared value of 85%, meaning it allows us to explain 85, almost 86% of the variability of our output. That's pretty amazing. And if we add just two more variables, namely displacement and number of cylinders, because gas usage is of course dependent on how big the engine is and how many cylinders are running, then we increase our fidelity of our model by almost 5%. That's pretty amazing. But we also know that if we are constrained in terms of processing power and in terms of memory, using just one variable, namely weight, will allow us to build a really good regression model, even if it's just a simple linear regression. Let's take a look at our equation with just one variable, which brings us back to a very simple linear regression. We're seeing that the residuals are centered around 0 and almost symmetrical, which means almost normally distributed. That's good. We're seeing that our p-value here is very small, and the most important indicator, namely our R-squared value, is indeed between 85 and 86%. So we can, in fact, save processing power, we can save memory in any computer that we're running this model in by limiting ourselves to one and only one variable from our data set as the predictor for our response variable, gas per 100 miles. Very good. Now let's see what this looks like in Python. We remember in the fuel efficiency in cars dataset that the attribute GPM, which is gallons per 100 miles, and MPG, miles per gallon, are essentially congruent, which means that we can drop one of these in order to make our processing easier and faster. This is exactly what we're doing right here. We're going to drop the MPG again so that our dependent attribute for the remainder of our analysis will remain gallons per 100 miles, or GPM. Then we are using this code in order to plot the independent variables against GPM. Here shown as an example is weight. Here's what a simple linear regression looks like with the stats models package. We first import the stats models package as SM, and then we declare our X and our Y, that is our predictor and our response, and we make sure that we add a constant as well. Then we build our model with the OLS, the ordinary least squares model for Y and X, and we're going to fit this model, which means we're going to build this model, and then we're going to pull out the summary. In the summary here, we can learn a whole lot of things. The first thing we're seeing is that our R-squared value is at about 70%. That means that 70% of the variation in GPM can be explained by using NC, that is number of cylinders, as the predictor. Secondly, we're seeing the coefficient table right here. The constant is 1.0581. And the coefficient for number of cylinders is 0.6, which makes our simple linear equation into GPM equals 0.6 times NC plus 1.0581. We're also seeing the other variables here, the standard error, our t-value, our p-value here with the confidence intervals. So this is the output of stats models, which gives you a very nice table. Here's what a regression, now a multiple linear regression, looks like in scikit-learn. First, we're going to have to import the linear model from scikit-learn. Then we declare our variables. For x, the input variables or the independent variables. Here I have selected all of the variables that I'm interested in from our dataset. And our y is the response variable, GPM in our case. After that, we build our linear model here, the multiple regression linear model. We use the linear model.linear regression function from scikit-learn and apply the model with lm.fit, lm being the alias that I've built here. Now, scikit-learn is a little bit different than stats models. It's not as pretty, which means that we have to retrieve any of the numbers that we are interested in. So here, for example, we can retrieve the R-squared score with lm.score. We're seeing that the R-squared score here is 91%. That is very nice. If we are interested in the coefficients for the predictors because we want to build the equation by hand, we can retrieve those with lm.coef underscore. And if we're interested in the intercept, certainly we can retrieve that with lm.intercept, also with an underscore. Awesome. Here is what we have discussed in this model. We have defined the linear model and we've lifted the cover on the math behind the model. We have determined when linear models are appropriate for data analysis, and we've used simple linear regression and multiple linear regression to build a model of various data sets and various data within these data sets. We've used R and Python to do so, and we have evaluated the models with important quality metrics, such as the R-squared value. Thank you so much for watching, and I look forward to seeing you again in a future video.